safety in design of lifting pattern. It is available in cloud-based and iOS environment. Yeah, the software calculates the stress state of the section of a pad eye. It calculates plot utilization factor in a user-friendly format. We can do manual or automatic operation. Out of plane forces, as I mentioned before, are always checked in accordance with standard requirements. Stresses around the plate, around the thick plate holes are also checked for minimum capacity using a numerical elastic formula. And this is the one that we like it. It's a photo of foreign. It's of a photo of a design drawing or actual fabricated pad eye can be taken by engineers, and then can be traced and review the stresses based on the material thickness and design loading. So this is some of the part of the appearance of the design. So we can produce, it can produce the design drawing for the maybe designer or drafter to make an AutoCAD drawing, and this shows the desktop of the application. And people are asking where has it been successfully applied? It can be used in designing, reviewing new pad eye and existing pad eye capacity. Has it been applied in a company? Yes, it has been used by engineers in major oil and gas company in this case. And then general review by users. Has a pro and cons? Yeah, the pro is unique features are user friendly, interactive, readily available, but of course depend on every user. The benefit is I mentioned before, it's to prevent catastrophic failure and lifting operation due to miscalculation of pad eye design and critical failure line. Economic solution in a pad eye. Any shape of pad eye with 4 stiffness can be analyzed. A quick assessment of pad eye capacity by tracing photo of a design drawing, and assisting engineers during design review and field fabrication. So then to improve productivity of the engineers. A direct report printing and pad eye analysis, design and sketches. So it will produce directly the the analysis and the report. What is value creation with this technology? What can we do better? We list some of the potential cost savings here. So of course, clear that avoiding lifting operation failure, catastrophic failure. We just estimate the company reputation value of estimated 1 or 2 million saving. So nothing happened. Safe, very safe operation that we save a bunch of money in US dollar here. And then the second one is optimizing engineers man hour by simplifying design process. A quick assessment and checking, so avoid repeating errors in lifting pad eye design. So basically, we are repeating the human error or engineer's error in designing pad eye to try to avoid that with the reasonable application. Right. Okay. Now we are going to the software itself. So let me try to go into the sharing the application. Right. Just to check here, can everybody see the pad eye designer screen here? Can see the screen? Hello,
yes,
everyone.
We can see your screen now.
Okay, thank you. Okay, right. So our software, our application here is uploaded to the cloud. So we use the remote access here. So we call it pet eye here. And another one is the MedCat. I think next time we will have some webinar also on the other software. So now we are going to look into this pet eye application. So this is the desktop, the front page of the pet eye. So you can see here, this is the picture or the drawing of the pet eye, one of the pet eye. So you can see here, this is the elevation. This is the section from this view, and this is from the top view of the pet eye. So we have some page here. Yeah, we call it auto checking page. We have the manual checking. We have the material and welding. This all showing the forces, stresses. So engineers can check, can verify what is happening in the pet eye. And this is load capacity around the hole. And this is the geometry of the pet eye. So this one can be input numerically. So for example, this one, a left length on this left side here. This is right length, if you see here. And we have some button here to verify or to simulate the load direction. And another picture here is the radar. We call it UF radar, utilization factor radar. So it's showing the 0, 2.5, to 1, and 1.5. So in a circle, so we know the maximum utilization factor for every stresses in every direction. So I give you an example here. You have a button here, shackle rotate. So if we rotate this shackle direction, so it will calculate the stresses on this section, on the bottom section of the pet eye. So you can see here the dotted line. So the location of the section right now is on the bottom. So when we rotate the direction, it will calculate all the stresses here. So the utilization factor of every type, normal stress, left, right, means left means here, right means there, and the shear stress in the main plate, this value and the allowable formations, left, right. So formations is around here, the extreme one, and bearing stress of the main and cheek plate. So basically, by moving this, it will calculate all the stresses of this. So right. So here, when we go that direction, this direction, it will calculate. So we can see here that the stresses is below 1. Sorry, the UF or the utilization factor, all of this direction that we run is below 1. And then, for example, we want to check in this section, for example, we can move the section up or down. This is, I'll show you, this is, so the section, you can go up and down. And then here at the bottom, it shows the cross-section area where the line is on. So you can go up here, until it goes up here. So you can see the main plate is on this part, and it will include also the main plate and the cheek plate. So it goes up, maximum will be on this line. So of course, we need to check only up to this because the forces is above this line. So you can see the extreme. And then if we want to check this line, for example, we go down a bit, this section. What is the stress stage or UF on this? We just move this shackle. Yeah. So you can see here the UF is lower. So basically the stresses here is lower than the at the bottom. Normally the bottom will be the what do you call it, the high stress, because the distance from the load application to the section is far. If you want to check at the bottom back, you just click here on the section at base. So it goes down to the base and then we check again. I'll give you an example here. The next page will show the drafting board, we call it. So we can change the size, for example, of the bed eye on the drafting board directly. So you just click on the number here and change, for example, the size. You can change anything here. We can change here the distance, and then we can change the diameter. Everything we can change here. So a click, the thickness and everything. So we can change here the width of the bracket. We can change the thickness of the cheek plate. We can change the thickness of the main plate. And you can see here the gap. It will calculate the gap of the shackle and this bed eye. If you can see, if you go back to the desktop here, you can see here, the blue one is the shackle and the gray one is the bed eye. So you don't have a gap here. So it gives warning. So the gap less than 3 mm. So we have to reduce the bed eye, the bed eye thickness. So then you can see here, there is a gap now. All right. So back to the stress state. It gives also us the line here. This is the critical line of the block stress that we are talking about. So the block stress calculation or determination is automatically calculated, depends on the geometry of the bed eye. As you can see here, load capacity around the hole. This is outside. This is the out of the cheek block shear. It gives this line. And this one is the double shear at hole, means this is normally when we design a bed eye, we need to check the double shear around the hole. And this one we also check the plate. I'll show you later how critical it is, or how critical it is. If you have a thin plate, and then so this line depends on the cheek plate diameter. So okay, back to the analysis. If we have like here, for example, we have low bed eye, low bracket here. We try to change the bracket, for example, down here, or we can make it smaller. We can change this smaller, and maybe we can increase. So everything we can change easily here, right? So what is the critical section in this design? So yeah, it's similar design from the previous, but now we have a lower bracket here, and then we have a smaller diameter of the cheek plate. Where is the critical section in this case? So normally the critical section will be still on the bottom, right? So we check this one. Okay, now we have the unity check or utilization factor around this area. But how about upper here? If we move this up a bit here, maybe, yeah. The distance now is closer, but the area only with the main plate here. So if we check, yeah, it gives us a higher utilization factor. But which one? And then we also have maybe an angle, for example. If we rotate the section, we rotate like this, and then make a bit up. What is the UF of every direction, for example? Okay, this is it. So we made this a bit. We have to do it manually. Now we try to do it automatically. How to do automatically? We have here the button, so we can change your angle of the minimum angle of this bed eye. So for example, we give a 90 degree, maybe 85 degree minimum angle, and 90 minus 5, this is 90, maybe 100 degree. So it will be between this and this angle. So then this app can do automatically to check the critical section from the bottom up to the hole. So by pressing the start stop here, it will automatically checking the stresses within this range of angle and within the range of the angle. So you can see here, it stopped at the maximum stresses that it found by automatic design. So you can see here, the final position of the section is here. So it means that this section is the most critical section. To give an example of extreme one, we can change, for example, the main plate thickness. This one, just go to the this. For example, we reduce the thickness of the main plate, and we go back to this, and then check the start stop again. Yeah. Right. So it will quickly simulate. So you can see here some red here. So it means that this is the section, critical section, which gives us the maximum stress. And then you can see here the UF is red, 1.6. The number is Jeff with this one. So yeah, you can change also the, if you want to check the angle from maybe from 80 degree to some degree here, 125 degree. Then you can have a wider action. So you can see here the wider, the wider range of the angle of force of the direction. Yeah. The more range, then the slower the simulation. And we can also change the how it goes, the incremental. For example, delta angle, we change to 10 degrees, for example, and we change the delta section by 5 degrees. The simulation will start, we change the increment by changing this number, right? Okay, so this is the drafting code. We can change anything. We can change the shape of the pet eye. We can change it, the shape of the pet eye like this. Yeah, we can change the pet eye. So if you have like this direction, for example, yeah, then we can change everything. Okay, we can do automatic, we can do manual, we can change the geometry of the pet eye by just dragging this, all the geometry. And another one is the shackle itself. Okay, we have here for the demo, we have a cross B type of shackle, and then it has the table of the shackle dimension. As you know here, it has the dimensions. D is the diameter of the pin, and this is the safe working load in tons of the pet eye, and all these dimensions, and the estimated sling size to lift to move the lifting, to use for the lifting. So we have like some table. It can we have an expanded shackle list, but this one is for the demo. So we can choose any pet eye. For example, we choose 800-ton capacity of pet eye. It will give us directly the initial design of the pet eye. So then we can check whether this okay or not. Yeah. So you can see here it's not okay because you have a red one here. So it shows also what is happening here. The normal stress at the left is high, is 1.19. So it's highly stressed on this side. So then we have to change the size. Maybe we increase the bracket and some of the bracket here. maybe increase, and then we can, okay, if you can see, we can zoom in and moving a bit here to make it clearer. Then by having this, let's check what is the, yeah, here now become green, but some direction here become red. So basically this pad eye is good for this direction only. For this direction, it gives us the high stress. So it looks like between this, for example, this degree, 80, 104, more than 104 will be green. So we can adjust this to 104, for example. Then we run the simulation. So we are limiting this to this limitation. Yeah. And then you can see here, it found out that this stress is the highest. So it has some red here. So it's why? Because it's got only main plate and some bracket behind. So this bracket is kept. You can see here is not used. So yeah. So yeah. So this pad eye is not adequate for this. So then we go back to the drafting board, and then maybe we can increase this to this height. And then we can increase a bit this side, go to the left a bit. Yeah, maybe we can increase a bit. Yeah, the size. Let's see how it happens. Start, stop. Yeah. So basically now it's green. So basically this pad eye is safe for this design load. Yeah. Another thing that I talked about is how to use the pad eye for the designing of an existing pad eye, or if we have a drawing, we can get a picture and then put in the system here. Yeah, this is one example of the pad eye design. What we are going to do is we try to trace using the existing drawing of a pad eye. The thing is very important is that we have to put the pad eye on the center of the pin. The other thing is the shackle. We have to choose the right shackle. For example, that I designed for 200 ton, for example. For this, then what we need to do is we need to make the holes the same as this design. So basically, you have to fix it on the center here. And you can zoom in and zoom out, see, to make the same hole, basically, because the pin is the determination, the showing the capacity of the pad eye and also our pad eye. So we just make the same here, right? And then trace it. So basically, sorry, this is zoom in. Yeah, we put together and on the center and zoom in, zoom out. All right. It's all black. So what we need to do is just change the color of the upper, so we can see the difference between those two lines. And then we change the size of the pad eye like this. So we change the pad eye, the height and everything. So basically we trace the pad eye so to make it the same size. So yeah, by doing this, we know that the dimension of the pad eye is same. Of course, the thickness of the pad eye we have to input here, knowing what is the design. And this is on the left side, we have to moving this and this direction. Yeah. So we can make it this one. We don't have this, so just make it 0. We don't have this one. We have this one. We can have this same direction, like this one, this one. So basically, once it's got the same tracing, then we should be able to know that what is the thickness of this bad eye. So then, by having this model, then we can analyze this bad eye. Okay, which is whether this bad eye is satisfying the requirement. Okay, looks like it's okay. So now we can run the automatic check. Yeah. So this bad eye having a critical section of this area. So why? Because of the distance and everything. So it automatically calculates the stress state on this section. So how about the section at the base? Of course, the section of the base will be like less than this critical section. And this data is not good for this direction because it becomes red. So basically, the bad eye designed for only in this range of bad eye direction. So if we run again, okay, it's just optimum that we have UF utilization factor just near 1, almost 1, so 0.99 here. So the normal stress is at the left side, so it's here at the left with UF of 0.99. Yeah. Another thing that I want to show you is we have also can do a kind of test on the actual bad eye. Hopefully, I will have the drawing here. Yeah, this is a photo of the bad eye fabricated in the yard. So same thing that we do before. We try to make the hole the same, but before that we have to choose a cycle that this bad eye is intended for the design. For example, 800 ton bad eye. So we go back to the drafting board, and then zoom it in, and then make the same, and then trace again as right. So then trace. Yeah, trace like this. This is the we don't think we have this, or we can put it here somewhere, and then we don't have this. We can remove this, for example. Just remove this. We can zero it, right? So this size we can change here, and then we can change here. So yeah, so you can adjust by having this drafting board. So see here, you can have the same size or same dimension as in the picture. So of course, we need to know what is the specification of the material of the main plate, cheek plate, and everything. You have to know the thickness. What is the thickness? Because from the picture we cannot see the thickness. Then we can measure it. And then here we have like 100 millimeter of main plate and 60 millimeter of cheek plate. You have to input. And then let's see if this bad eye good enough for the load. No. So you can see here it's red here. If we run the start stop button here, it gives us a red utilization factor. Means that we have overstress somewhere. Oh, this one showing on the right, which have a 1.4. So this one looks too small. We need to widen it. So we can widen it here, maybe. So this needs to be widened, and this one may be somewhere here. So let's check again. Yeah, it reduces, but still have some overstress. So maybe we need to, it's already very thick here. If it's thicker, then it might, it might problem with the gap. So maybe we need to widen it and thicken it, kind of 760 mm, and then check it again. Yeah, this is just about to meet the requirement, so we need to make it thicker, maybe, or make this one maybe wider. Yeah, it's a bit too small, maybe. Then we can double it. Then let's see how it works. Yeah, except this area, maybe. Why is it? Oh, you can see here that the section, critical section, so in this area. So by increasing the height of this, it might solve the issue here, because it's just cutting the line here. And this doesn't include the second stiffener or second brace bracket. So this bracket is a bit low, so we can increase this one up to here maybe. Then we can recheck how it works. Yeah, so it goes here. So basically, here you can see that the extreme stresses or the maximum stresses is not necessarily at the bottom here, but maybe somewhere up there. So we have to be careful that, okay, this one is not included, this two is not included in this section. So we might need to change the design of the bed eye, or taken the shape, or taken the main plate maybe. Let's see if we need to taken the plate a bit. Then yeah, start again to check. Yeah, it still goes to this direction, to this section, but we have a we have a less than one utilization factor. Okay, so this is basically how it works. And also we have the weld of the main plate here calculation. So it gives us the minimum weld thickness. So basically it's 40 mm for this one, for example. It gives us a minimum 40 mm welding, fillet welding on the main plate to the bottom. And the cheek plate, we need to have like a 12.8 or 13 mm on this, around the what the cheek plate. And yeah, I want to like talk a bit about on the capacity around the hole here. Right, this numbers showing the load on this hole, and then the capacity of this area. If we go back to the, I think small, it's clearer on the small bed eye, for example. We can add, and then we go to this desktop. Okay, this line, the dotted line, is calculating the capacity of this bed eye based on the block shear here, and also the utilization for that what you call it, the stress state. So here you can see this line will change depends on the inclination of this, because the block shear will change. It depends on the direction of the load. For example, I'll give you the example here. You can see here it's in this direction. If we change the slope of this, for example, to this angle, and then this one to this angle, yeah, you can see here it's trying to be perpendicular. So it's trying, this is the minimum minimum area which gives us the maximum stress of the block stress. So here you can see it's okay, because the utilization factor is 0.27. If we check around this again by running this analysis, this that I think we should go for minus 4 for 85 to 200, for example. Okay, this kind of symmetrical pattern. So you can see here the critical line is this one, but UF rated is okay. So it means this pattern basically works for all aspects. But if you try to change, for example, the thickness of the main plate to somewhere thinner, and that how does it go? Let's see what happened to this pattern. Yeah, still green, and the capacity is still there. We can change maybe the it goes up. If we want to change, for example, this to higher. No, it goes to higher. Okay, the load factor we want it to 3. Yeah, it goes to this. Kind of change is just a test. Okay, this become red here because this area will fail instead of double shear here. If you know the shear stress, then because of the thickness of this very thin main plate, it will fail on this one instead of this. So we have to check also. Instead of checking that we need to check both the double shear on this side, on this thickness, main and the cheek plate, and also basically we need to check around the cheek plate, because it's here you can see it's giving us a lower capacity than the load itself, so it gives us the utilization factor of higher than 1. Okay, so this is one thing that it's not captured in this radar, so we need to check everything here, which one is red, which one is not red, basically. Yeah, I think that's all for now on the explanation. Yeah, if you have questions, then we can open some Q&A after this. Thank you very much. Appreciate for your attention in this case. Okay, Mbak Dian, Mrs. Dian sendiri. Yeah.
Thank you so much, Pak Suryatin, for your explanation. And then now we have several questions here, and I hope that you can answer one by one according to our software engineering for PET ICE. So let's start from question number 1. What code or standard does the software use to do the calculation? So what code that we use for our software?
Yeah, I can answer directly. We use the API and the AISC standard, but I don't know, Mr. Who somebody talk about the
ASME. ASME
yeah,
standard.
ASME standard. Yeah, we can incorporate that. Yeah, we think we can incorporate that into the software. Thank you very much for the question.
Okay, I hope that someone who asked about this question already understand about the answer. And then the next question is, this PET ICE design is using WSD or ASD approach only, isn't it? Can it modified for ISO or LRFD approach?
Yeah. Okay. Honestly, we developed this PET ICE using WSD code. So we are going API WSD and also the ASTM code. So it's a standard, it's a WSD, it's a working stress design.
So can we modify this for ISO standard?
Yeah. It can be like it can be modified. Yeah, based on the the requirement from the community or from the engineering perspective. It will be the client if we want to change or to add additional features that we can check with the LRFD. Yes, we can do it. For now, this application is use the WSD approach.
Okay, this question is from Pak Tatang Soeharto. So Pak Tatang, I hope you satisfied with the answer, or if you still want to ask something, you can raise your hand or unmute so you can speak directly to Mr. Suryatin. And then the next question is, how we design fillet weld on the bottom and fillet weld on the stiffener. This question from Pak Ferry Sitohang.
Yeah, okay. Normally, the welding design is using shear approach. It's a normal design. So calculating the shear on this area, and then calculating this on the shear on this area, and also shear on this area. Based on that shear, maximum shear forces and the area, it will come up with the weld size, the fillet weld size. And of course, also depends on the weld strength. In this case, we use 355, for example. If we change to 450, then you can see here, it will change the size of the what do you call it? The welding. Yeah. It basically normal calculation. It will calculate the maximum shear that's happening. So then it will calculate the thickness of the welding. Yeah. Thank you for the question.
Yeah. So the next question is, can these apps be used for calculation of existing pad ice? So it's not only for the new one, but also the existing. I think that we can use it also for the existing one, right?
Yeah, sure. That I showed here on the drafting board that we have a trace. This is the existing pad eye. So trace it, and then trace using this method, and then we can change the. We can trace with this. Okay, basically we change to fit the hole first, and then we change the other dimension.
Okay. Yeah. So I hope that Pak Mulyana, you satisfied with the answer, so you can use also the software for existing pad eyes. And then the next question is, how about sling without of plane angle?
Sorry?
How about sling without of plane angle? The question from Mr. Sherry.
Without plane angle. Sorry. Okay.
Without
this here.
Plane angle.
Without plane angle. Okay. So here we have the input of the out of plane load degree, for example. Okay, let's check on this one. This is red because it's too thin. We change the main plate to, for example, 15. Yeah, make it 15. Okay, still red. So come back. I think come back to the 25, standard 25, and then check it. Oh, still red. Oh, I think because of this 2, we get 2. Yeah, green, so no failure. Yeah, this is, you can see here the button or the text. We can change, for example, this is green already for this load direction. But if we change this out of plane to 15 degree, you can see here it become red because of the out of plane bending, causing this overstress here, down here. So with 15 degree load out of plane load with a 15 degree angle out there will give us the overstress. So if we check again on this, yeah, it will become red all. So yeah, basically we can do it. So 0 degree, yeah. But if we go to 0 degree, it will give us a warning that out of plane angle less than 5 degrees. Normally, we have in the design, we have to allow for 5 degree out of plane. So it will give us a warning, even for example, this one green, but it gives us a warning here. So it's not supposed to be less than 5, for example. So 5 degree will be okay. Then we check again the prices. I think that's answer. Hopefully that answer the question. Thank you for the question.
Yes,
Next
I hope
question.
Sherry can satisfy with the answer. And then the next question, I know that someone already raised hand, but we will come back to you after we finish read all the question. So the next question is, in this software, how about type material we feel about yield strength? So I think that Mr. Jefferson asking about yield strength for the material using this software.
Okay, the yield strength is defined here in the material and welding. So, for example, this one is green, hopefully. Yeah. We change to, for example, 235. Let's see what happens. Yeah, it become red here. So the material is a bit too low here. So it gives us the bearing stress, over stress here, 1.2, and the normal stress. So you need to increase, for example, to 355 material for this design. And then also the cheek plate, of course, the cheek plate we can have a 235, for example, yield strength. But this one will only affect the bearing, for example. Yeah, you can see here the bearing is red because the cheek plate is failing. I mean, overstress. Yeah, so we need a bit higher 355. Oh, sorry, 355. Yeah, it gives us the UF of 0.81. Hope that answered the question.
Yeah. And then the next question from Pak Bashar, how to get the software demo license and price. So this is marketing question. So for all of the information after this webinar, we will send it to you, information how to get a demo license and also pricing option and etc. And after that, for the next class, we will invite you again, and then we can run together the software, so we understand exactly how to use the software. And then Mr. Suryatin will guide us. But I think that this is for a limited code. So I think that for the first, we can do for 20 people, I think, Pak Suryatin, right? To make focus or...
Yeah, for now, I think we can give 5
Okay,
license,
so now
5 demo.
yeah,
for
so
5 demo. I
should
think
be...
sorry to be like first come first.
Yeah. This is should be limited, but we will keep going every week to explain and to invite you to use together with us for this software. But you have to register soon as possible, because it's only a limit for 5 people in every season. Okay, Pak Bashar. So, but we will explain. We will send email to all of you about the price and how to get the license. And then the next question, I think that Mr. Tatang Suharto already helped us to write down all of the standard code. So thank you so much, Mr. Tatang Suharto, to help us. I think that is only the question. So now we come back to Mr. Ferry Sitohang. You raise your hand. You can ask your question directly to Mr. Suryatin. So Pak Ferry, go ahead.
Thank you. Thank you, Miss Miss Dina. One my question regarding to the stiffener. How about we decide the fillet weld between the main plate with the stiffener? So if you already explained about the welding between main plate to the existing structure, but how we decide the minimum welding, the fillet size of the main plate to the stiffener. This is I want to know from your software, because I see from your current presentation only show the welding size between main plate to the bottom, right?
Yeah.
But I didn't see on your screen presented the welding size between main plate to the stiffener. Thank you very much.
Okay, thank you for the question. Good question. But basically, if you have designed the main weld on the on the main plate to the object is strong enough, then basically you don't need the weld from the bracket or from the stiffener to the main plate, because the main plate, the bracket is just to resist the lateral force. So basically the compression or the thickness of the main plate can sustain even without welding. So it won't give us the stress on the welding. I think I hope you understand what I mean. So the main plate welding to the object is good enough to resist the force, but as you know, of course, the bracket needs to be welded to attach to the main plate. So basically, minimum fillet weld of the bracket or the stiffener to the main plate should be adequate, minimum welding. Because there's a standard, for example, a quarter of an inch welding should be practical, or half an inch should be practical. So yeah, basically that's my answer is. Okay, thank you for the question, Pak Ferry.
So I think that we already answered all the question, and then our plan was only 1 hour, and now we already ran for 1.5 hours. So if you have any question, please welcome. If not, so we will stop our webinar, and then keep in touch with us and stay tuned in our LinkedIn page, because we will send you announcement to invite and then run together how to use this software, because this is only limited for 5 people in every season. So stay tuned, and then who register first, so they will join with us. So thank you so much, everyone. Thank you so much, Mr. Suryatin. I appreciate for your explanation for this software, and also to all our participants. Thank you so much for your time. So see you for the next webinar, and stay tuned and get connect with us in our LinkedIn. Thank you so much. All the best and stay safe.
Thank you very much all for the attention. Okay, hope we will see you all soon.